Hello, good afternoon, good day. Welcome to this lecture video. I'm Teacher Melai and let's talk about frequency measures. So in our previous lesson, we discussed measures of central location or measures of central tendency, which includes the mean, the median, and the mode. So when we use this, we actually come up with a single value that can summarize the entire distribution of the data. So aside from that, I also ask you to come up with frequency count and percent distribution of your profile variable. So you were able to gather your data, and using your data, you come up with a frequency count and percent distribution. And the formula for you to compute for the percent value is the frequency all over the sample size or population, rather, if you are conducting a population study, multiplied by 100%. Of course, here it is also similar in a way that we are also dealing with the same formula. It is numerator all over denominator, except that it is multiplied by 10 raised to n. So it can also be 100 if n is equal to 2. Now, the commonly used frequency measures are ratio, proportions, and rates. So if we will just recall for the value of 10 raised to n, if it is 0, we know that if a number is raised to 0, it is always equal to 1. And 10 raised to 1 is the same number, it is 10. 10 raised to 2 is 10 times 10, it is 100. 10 raised to 3 is 10 times 10 times 10, 1,000. We usually use this in cases that, for example, it is in decimal numbers and it is hard to picture what it means. Like, for example, the value is 1.5. So instead of coming up, especially that we are talking about person here, so instead of dealing with that percent, the tendency is we multiply it, for example, by 1.5 times 10, so it is 15. So 15 per every 10 cases. So it has something to do with how to picture it later, because it's of course not possible to come up with a zero point 0.5 or zero point 0.2 cases, because we are always referring to person. So the fractions of or the numerator all over denominator can be multiplied by 1, 10, 100, 1,000, and so on. So in our next discussions, we are going to also to try to figure out what are the commonly used 10 raised to n value for whatever is asked to us, asked for us to compute. So here, just to give you a brief definition of what is a ratio, it is a relative magnitude of two quantities or a comparison of any two values. It is calculated by dividing the one interval or ratio scale variable by the other. So the formula here is number of rates, number or rate of events, items, person, and others in one group. And over number of rate of events, items, person, etc. in another group. So after the denominator is divided by after the numerator rather is divided by the denominator, the result is often expressed by 2, 1, or written as we have the colon sign and 1, this one. Okay, so we use this in different categories. So it can be categories like the one I asked you, the profile. It can be age brackets and all other possible variables that can be related now to some health concerns or in hospital demographic profiles. So this is an example of a calculation of ratio. So we have here original enrollment value wherein we have diabetic men, non-diabetic, then diabetic women, non-diabetic women, ended at follow-up. So the data are obtained in 1971. It's data from 1971 and 1975, and also data from 1982 to 1984. So it is based from the National Health and Nutrition Examination Survey conducted. So in this data, we can compute for the value of ratio by, for instance, if you are asked to calculate for the ratio of non-diabetic to diabetic men, then you will just simply divide, so 3,151, this value, over 189. So we are referring to our original enrollment multiplied by 1. So it is 16.7 by 1. Or if you will multiply this by 10, then you actually need to change this by is to 10. So 167 is to 10. So it can also be like that. So it depends now on what will you multiply. Here, you can multiply it by 10 because simply because 16.7 can be rounded into whole number by multiplying this, or rather, so by not just rounding this off to 17, because zero point 0.7 is quite a large value. So what you need to do is to multiply it by 10, and of course also the 1 here will be multiplied by 10. So we have here the following properties and uses of a ratio. So ratios are commonly descriptive measures. It is used in all fields. In epidemiology, ratios are used as both descriptive measures and as analytic tools. So as a descriptive measures, it can describe rather male to female ratio of the participants in the study, the ratio of control cases, example, to control per cases or per case rather. So as an analytic tool, ratio can also be calculated for occurrence of illness, injury, or death between two groups. So these ratio measures include, so if we are going to use ratio in analytic analysis later. So the commonly used are rate ratio, odds ratio, and which will also be discussed in a separate video. So as noted, numerators and denominators of a ratio can be related or unrelated. So in other words, you are free to use ratio to compare the number of males with the number of females, or to compare the number of residents in population with the number of hospitals or dollars spent on over-the-counter medicine. So, but of course, you have to think of the purpose why you are actually doing that ratio. So it can be based on your analysis or based on the making decision that it is enough, that the, for examples, the rooms are enough to accommodate all the patients with particular disease. So something like that. Or the number of available inventories of medicines are also enough for you to cater, or for the hospital to cater the patients. So usually, the values of both the numerator and denominator of a ratio are divided by the values of one or the other, so that either the numerator or the denominators equals 1. So the ratio of non-diabetic to diabetic, for example, and the given example is 16.7 is to 1, then 3,151 is to 189. So instead of just mentioning that for every 3,151, there is 189, so you have to divide it in such a way that you can come up now with a value that equals 1, and that is dividing both sides with the value 189. So that 3,151 divided by 189 is 16.7, and 189 over 189 is equal to 1. So as I mentioned in the properties, we can also use ratio in different variables. So such as, for example, number of persons in a city and the number of clinics. So if you want to make a picture if how many can be catered now by the clinic, or if it is possible that the clinic be that all the persons in a city can be catered, then you can also make a projection of this. So for this example, it is 50 all over 4,000 times 10. This is 10 raised to n. It's 10 raised to n. So we have here the value equals to 0.0000125 clinics per person. So it's actually different to get a picture of it. So to better understood it, so instead of using 10 raised up, simply 10, you can raise 10 into 4, and that is 10,000. So which means if we multiply 0.0000125 by 10,000, it means it is 1.25 clinics per 10,000 person. Or you can also say that since it's 0.25, or if you want it to get a picture of a whole number, so you can remove, because 0.25 of 10,000 is somewhat in what do you call this, 2,000. So you can actually express this into one clinic for every 8,000 person. Or if you divide 1.25 by 1.25 and 10,000 by 1.25, so you can also get the value that one clinic is for every 8,000 person. So we also have here another example also for infant mortality rate, which is 10.7 per 1,000 live births. So New Hampshire infant mortality in 2001 was 3.8 per 1,000 live births. So calculate the ratio of the infant mortality rate in Delaware to that in the New Hampshire. So just to give you the solution, so it is just simply dividing, of course, 10.7 by 3.8 and multiplying it by 1. So that is 2.8 is to 1. So which means that Delaware's infant mortality rate was 2.8 times as high as the New Hampshire infant mortality rate in 2000. So you are having a comparison here between the Delaware's infant mortality and the New Hampshire infant mortality. Okay, so we have a commonly used epidemiologic ratio, and that is the death to case ratio. So what is a death to case ratio all about? So it is the number of deaths attributed to particular. This is during a specified period divided by the number of new cases of the disease identified during the same period. So the challenge actually here for you to use all of this is that the validity and also the reliability of the numbers that you're going to get, and of course how to get that number. So that's the challenge, because the formula itself is very easy. That what you need to do is just to divide it. Okay, so how about for proportion? Okay, so let us first consider an example here. So in the United States in 2002, so we have a total of 15,075 new cases of tuberculosis. So during the same year, 802 deaths were attributed to tuberculosis. So the death to case ratio for 2002 can be calculated by, so the number of death is 802, And new cases, total of new cases is 15,075.